Hello and welcome to lecture number 13 in the course Advanced Robotics. In the last class, we looked at the chapter on redundancy resolution. That is, in a redundant manipulator, when you have a large number of degrees of freedom and you have to perform a task, then you can divide the task into one major task and then a subtask. Now that basically happens because you look at the Jacobian of a redundant manipulator. It is non-square matrix, which means that if you want to take the inverse of that, you will not get an exact inverse, but you'll get a pseudo inverse, which means that there is always an associated error with that, which is in the form of the orthonormal basis vectors, right? So today we'll continue from there, and we have been talking about kinematics of manipulators. Slowly we'll move towards dynamics of manipulators. Now in dynamics, what we'll see is that when a manipulator moves in 3D, then what happens is that the velocities propagate from one link to another link. What does that mean? That means that if you have a 3 degree of freedom manipulator in which the base joint is moving, but the forward two joints are not moving, okay, even then, because the forward two joints are not moving, even then those joints will be having velocity, okay, angular velocity and linear velocities. Okay, so we see that velocities propagate from the base link to the forward link, and in terms of Jacobian, we saw that if you have an end effector force, then the force which is acting at the end effector propagates backwards into the joint torques. That means the force acting at the end effector will cause torques in all the lower joints up to the base joint. And in terms of velocity, the velocities propagate outward. That means from joint 1, it will go to joint 2, joint 3, joint 4, like that goes in the forward direction. So today we'll look at this concept of velocity propagation from link to link. Then we'll look at acceleration. And after acceleration, then we'll move on slowly towards dynamics. Now, dynamics considers the torque acting at the joints, which is composed of the inertia component, the Coriolis centrifugal component, and the gravity components, and could be external forces and friction. Now, to go to dynamics, we need to see how the velocities are propagating and how the accelerations are propagating. Okay, so today we'll move on to the next chapter, which is velocity kinematics, and we'll see how velocities propagate from one link to another link. Okay, so today we'll be talking about velocity kinematics, in which we'll see that how the velocities propagate from one link to another. So let's just to give you an example, or just to draw a diagram to clarify what I was saying, is we have a link here, and let's say this is 3 degree of freedom planar, just for example, and this is subjected to velocity theta 1 dot, angular velocity. Okay, now let us say that link 2 is equal to 0 and link 3, theta 3 dot, is also equal to 0. Now, because theta 2 dot and theta 3 dot are 0, okay, but because theta 1 dot has a particular velocity, what will happen? This velocities will propagate in that direction, and theta 2 dot will start having a velocity because of theta 1 dot. Similarly, theta 3 dot will start having a velocity, or the joint 3 will start having a velocity because joint 1 has a velocity. Okay, this is what we mean by propagation of velocity from the base link to the forward link. In the case of end effector forces, we saw that if you have a manipulator like this and there is a force acting there, then this force will cause a torque on this joint, and it will cause forces and torques. Similarly, this is going to propagate in this direction, and it will come from this joint to the previous joint, then to this joint, and then it will come to the base joint. So forces are propagating in that direction, velocities are propagating in this direction. Okay, now when we talk about dynamics, the dynamic equation is written in the form tau, that is the forces acting at the joints, is equal to the inertia matrix into acceleration plus the Coriolis centrifugal forces. So let's call it H, the H matrix, H theta and theta dot, which is proportional to the aura function of the position as well as the acceleration, plus you have the gravity terms, which is C into theta. Plus there can be other external terms, so J transpose F, plus there can be others external forces plus friction. Okay, so let me call this friction forces. Okay, so these are all the forces which are acting at the joints, or the components of the torque which is acting at the joints. Now this is my inertia, so this is the inertia component, this is Coriolis plus centrifugal components, this is gravity component. Okay, this is external forces, and there is friction force. Now you can see here that your inertia component, to find the inertia component, we need to compute the accelerations. Okay, so when the links are moving in space, we need to find what is the position, velocity, and acceleration. Acceleration for finding the inertia forces. For finding the corollary centrifugal forces, we need position, we need theta, and we need theta dot. Okay, and to find gravity forces, we need a theta, which is the position of the joint. Okay, so basically what we need is we need theta dot, and we need theta double dot. So position, velocity, accelerations are all required when the joints are moving. Okay. Now the interesting part here is that a joint may not be moving, and yet it may be subjected to forces and torques because the previous joints are moving. So it appears, or it is very clear from here, that every joint has an effect on the other joint when it is moving. Okay, so the joint itself may not be moving, but it will still be subjected to torques, or forces and moments which are coming from the other joints. Okay, so first we'll look at velocity, then we'll start slowly moving towards dynamics. Okay. So some of this you might have studied, but in robotics, this is motion of body in three-dimensional space, so they could be a little bit different. So please revise this carefully as we go along. I'll revise it also. So linear velocity, let's say that we have a frame which is fixed. This is my frame A, which is fixed. And let me call this frame A. And there is a frame B, which is there. This is my frame B. And there is a point which is point Q is given there. That's my point Q. Okay. So there is a point Q which is specified in frame B. Now there is a rotation and a translation between frame B and frame A. Okay. So frame B is rotated and also translated. Okay. Now in frame B, we have to assume that Q is a point. So Q is a point in frame B. Okay. Now this is and what is the distance between the origins? This we know. This is my origin distance between is APB ORG. Okay. So the distance between the origins of A and B is given by APB ORG. This we have seen before. Okay. Now for the moment, we'll assume that the rotation of A or B is not changing. So this means that orientation of B is not changing with respect to frame A, because we're talking of linear velocities here. Okay. Now, so the linear velocity can be because of what? Here, the linear velocity can be because of APB ORG changing. So the frame B is moving. So this is changing. So linear velocity can be because of change of APB ORG, or BQ is changing. Okay, that means the point Q in B is having a velocity in frame B. Okay, and or the distance between the origins of frame A and frame B are changing. So it can be because of this, or it can be because of that. It can be because of both of them also. Okay, so solving the linear velocity of point Q in terms of A is very simple. We just express both components of the velocity in terms of A. Okay, so what this is BQ. So what we can do is in terms of A. So let me write in terms of A. So A, velocity of the point Q in terms of A is equal to velocity of origins A, B, ORG. So that is the change of is the linear velocity between the origins of the two frames A and B, plus if the point Q is changing in B itself. So we put a rotation matrix there and say that if this is B, VQ. Okay, that is this part. So the linear velocity of the point Q can change if the distance between the origins of the two frames are changing, or if the point Q is itself moving in frame B. Okay, so we multiplying that with the rotation matrix and expressing that in frame A. Okay, please note that the relative orientation between B and A is fixed. Okay, then we can talk about this as in terms of a linear velocity now. So now I hope you understand what is a linear velocity, and the linear velocity of the point Q, which was because of the change in the origins of the velocity of linear velocity of the origins, or because the point Q was itself moving in frame B. Okay, and the orientation, please note that the relative orientation between B and A is fixed. That cannot change. Now, so much for linear velocity. Let's talk in terms of the rotational velocity now. So rotational velocity, or what we call angular velocity. Okay, what is an angular velocity and what is a rotational velocity? Again, one of the frames has to be fixed. Okay, so I'm drawing a frame here, the frame A, which is the fixed frame. Now we have another frame, let's call it the B frame. Okay, there is another frame like this, which we can call the B frame. Okay, now this B frame is rotating about an axis. Now let us say this B frame is rotating. So this B frame is rotating about this axis with an angular velocity a omega b. Okay, so B is rotating about an axis, okay, with an angular velocity a omega b. Okay, now I hope you can imagine if you are sitting on, let me imagine that you are sitting here. Okay, you are sitting on frame A. Now frame A is not moving. Frame A is the reference frame. Okay, so you're observing. What will you see? You'll see the frame B, which is rotating, because frame A is fixed, it's not moving. Frame B is rotating about this axis. So now if I have a point, let me say I have a point here. Okay, this is a point. Let me call this point BQ. BQ means the point Q in frame B. Now this is my position vector, which is BQ. The point is Q in frame B. Now if this is rotating about an axis, about this axis marked in red, what will you see? This fellow, because frame B is rotating about that axis, it will take a circle like that. I hope you can imagine that. Okay, so if you're sitting in frame A here and you're observing this point Q, what will you see? The frame B is rotating. What you'll see is that this point Q is rotating along with the frame B and is rotating about this axis. So what you'll see is that it'll take a circle like that. Okay, so now because it is taking a circle, what we see is that it has an angular velocity, but it also has a linear velocity. Okay, now why does it have a linear velocity? Now let me draw this again. So this was my axis of rotation. This is the circle. Okay, and this is the point which was there. Let's say the point is here. Okay, now this is the center of the circle, and this is the vector. So after a very small interval of time, let's say this is the circle that I just drew some time back. Now for a very small interval of time, this fellow will go here. Okay, so it will have this distance which it has traveled. This is delta Q. So the point was Q was here. This is my Q. After a very small interval of time, del T, this point has gone here now. Okay, now what I want to find is, if I say this, so del Q is the linear velocity. So it looks like it has moved in a linear fashion there. Okay, so now this is my QT. Okay, this is my angle theta. Okay, so let me make this small construction. Now what we see is that this is highly exaggerated. This is very small del T only. Okay, so what we see here is that what is del Q equal to? Del Q is this distance. Okay, del Q is this distance, which is equal to R into del theta. So this distance is, if I say this theta and this is my R, then del Q is equal to R into theta, or very small angle will be del theta. Let me call this angle del theta. Okay, that is the distance del Q which it has moved. Now what is del Q equal to? What is R? R is equal to Q sine theta. Okay, so if this is my angle theta, that is R, then it is equal to, so R is equal to Q into sine theta. This is my angle theta. Okay, so this distance R is equal to this vector, which is Q into sine theta, which is equal to R. So this is equal to a cube sine theta, which is equal to r. And what about del theta? Del theta is a small distance. Now it is traveling with an angular velocity a omega. So the distance is going to be a omega b into del t, that's small time. So for the small time, it has covered this much distance. So this angle is equal to a omega b del t. So this is a qb sine theta into a omega b del t. Okay. Now, and this has been covered in how much distance? A small amount of time del t. So if I divide both sides by del t, then what will happen? Del q by del t is equal to aq sine theta a omega b into del t. Both sides by del t will cancel. So this is my angular velocity. So a vq is equal to a omega b cross aq. Okay, this is what we call by the angular velocity. This is my the linear velocity because of the angular velocity which is given here. So what we see is that when a body is rotating, it has an angular velocity, there is a linear velocity associated with that. Why? Just because this is the body is rotating, okay, which is equal to a omega b into aq. Okay. Now in a general case, the vector q could also be changing with respect to frame b. This vector q, which is in frame b, I had drawn, please remember here, this vector q is in frame b. Now it could also be changed, this q could be changing with respect to vector with respect to frame b also. So in that case, what we can do is we can add that change also and say that the total velocity is equal to, in case it is changing with respect to frame b, plus a omega b cross aq. Okay. And if we remove the dual subscript, and noting that the description of aq at any instant is can be represented with the rotation matrix, then a vq is equal to arb. I'm just adding the rotation matrices. b vq plus a omega b cross a br into bq. So here it is aq. To convert it to bq, then I just have to put the rotation matrix, right? So this is considering the velocity of the point moving in frame b expressed in a, plus the linear velocity because of the rotation. Okay, so this is basically giving us a relationship between the angle. This is basically telling us the linear velocity of a point which is rotating, which is sitting on a link which is rotating. Okay, so we see that in the previous case, when I had explained about the rotation, just because this has angular velocity theta 1 dot, it will be having theta 1 dot plus it will be having a linear velocity also. You can call this v1. Okay, so it will, because of this point will also have a linear velocity. Okay, so when it is moving, not only the linear velocities are moving, even the rotational velocities and the linear velocities are both moving, okay, from the base link upwards. Now let's look at a few more relationships between this as we move along. Okay, now let us look a little bit more on angular velocity. Why? Because we were basically talking about the rotation matrix. Okay, we talked about the rotation matrix ARB, which is given in case of cos minus sine cos 0 0 1 0 0, and that is my rotation matrix. Okay, so there has to be some relationship between the rotation matrix, okay, and the angular velocity matrix. Why? Because this is a rotation matrix, so if I differentiate it, I should get a component of, I should get velocity, isn't it? Angular velocity. So let us see what is the relation. For that, let's look at the property of the derivative of orthonormal matrix. So this is a property of orthonormal matrices. We know that the rotation matrix is an orthonormal matrix. So if I write R is given here, right? R into R transpose, this is equal to the identity matrix I. We know that the orthonormal matrices. So R into R transpose, or R transpose R, is equal to I. Now if I differentiate this matrix, then I do get R dot into R transpose plus R dot T is equal to 0. Entity matrix derivative is 0. What am I trying to do? If I take the derivative of the rotation matrix, I should be getting an angular velocity matrix, right? Because they are related. So if I define this as, so from here, if I define S is equal to R dot into R transpose, okay, then I get, so I can write this as R dot into R transpose plus R dot into R transpose, the whole thing transpose is equal to 0. So if I take this, it will come back to that, right? So I'm writing this as S plus S raised to T is equal to 0. So this is what we see, is that S is a skew-symmetric matrix. Hence, a property relating the derivative of orthonormal matrices and skew-symmetric matrices exists, and this is stated as S can also be written as R dot into R inverse. Okay, so S is a skew-symmetric matrix. So we are saying that S is a skew-symmetric matrix, which is given by S is equal to, this is 0 minus omega z omega y, this is omega z 0 minus omega x minus omega y omega x 0. Okay, and this matrix can, and where omega can be written as omega x omega y omega z, and this matrix is basically called the angular velocity matrix. This is called the angular this is called the angular velocity matrix. Now can we derive the same thing from our rotation matrices, because they are related? So let's look at the rotation matrix now. Now the velocity of a point due to a rotating reference frame. Okay, so now if you have a reference frame like this, so in this point, this is my frame A, and there is another frame which is frame B. This is my frame B. Let's say this is my frame B. Okay, it's my frame B, and you have a point. Let's call this point Q. So the rotation matrix, if this is my vector Q, then AB, what is this rotation matrix giving us? This rotation matrix is giving me the relation of the point Q, the coordinate of the point Q with respect to frame A, although this point Q is expressed in frame B. Okay, so basically what we are saying is that the point A, or the point P, sorry, let me call it the point P. The point P expressed in frame A is equal to RAB into BP. Okay, so you have AP and you have BP. Okay, and the relation between these 2 points is given by the rotation matrix AB. Okay, now if frame B is rotating, then AP will be changing even when BP is constant. Okay, now frame B is rotating. So if frame B is rotating, then what will happen is I can take the derivative of this. Okay, so A is equal to ABR dot into BP. So I take the derivative of this equation. So on the left hand side you get the relationship, you get the coordinate of the point P in frame A, which is changing, so you get the angular velocity there, plus the rotation matrix, which is I'm taking the derivative of that, plus BP. Okay, so this one I can write as, now from here, so from here I can write AP so the angular velocity of the point A can be written as this matrix ABR dot, which is this one. And what is BP from here? BP is equal to ABR inverse into AP from this equation. So this BP part I'm putting it here, and what I'm getting is BP part I'm putting, so I'm getting ABR inverse into AP. Okay, so here again we see that we end up with that matrix. So VAP, velocity of the point P, is equal to this matrix, and this matrix is equal to what is the S matrix? S into AP. So this matrix R dot into R inverse is equal to this matrix. Okay. R dot into R transpose or R dot into R inverse is the same thing. So what we see is that we can derive this in two ways and get this as Q-symmetric matrix. Okay, so this Q-symmetric matrix is basically called the angular velocity matrix. Okay, now let's move on from here. So what we have seen is two things. First is that if a link is rotating, then the angular velocities propagate from one link to another in the forward direction. And if a link is rotating, it also causes a linear velocity in the forward direction. Okay, so there is propagation of angular velocity as well as linear velocities when the links are moving. So let's see how this velocities move from one link to another link, and this is basically called the velocity propagation from link to link, and that is something which we'll be seeing now. Let's talk about the velocity propagation. Okay, now why is this required? This is required because to do dynamics you need to know velocity, position, as well as accelerations. Okay, so we need to see how the velocities propagate, and then we'll also have to see how the accelerations propagate from one link to another link. Okay, so first let's look at the velocity propagation from one link to another link. Let's draw a generalized link system. So this is a generalized link. So this is one link and there is another link in front. So this is the forward link. Okay, so now this is my link. Let's call this link I, and let's call the link I plus 1 the next one. Now we can assign our frames. That's something you have that you know. So this is my Zi or Zi minus 1, whatever. The next one is this is my Zi plus 1. Okay, in this case. So now we see that there are angular velocities which are acting at this point. Let's say there is an angular velocity which is acting in here, this omega I. Okay, we are writing 2. So what does omega I mean? So I means omega of ith link expressed in ith frame. This is the meaning of omega I. Okay, similarly omega I plus 1 would mean the same thing. Okay, so we have angular velocity omega and I have a linear velocity which is VII. Similarly VII means the velocity of the ith link expressed in the ith frame. Okay, and on the forward direction here we have the angular velocity which is here omega I plus 1, and here it is VI plus 1. Okay, omega I plus 1 in the ith frame. Okay, so basically what we are seeing is that the velocity of the previous link is omega I and VI, and the velocity of the next link is omega I plus 1 and VI plus 1, and there is a distance between these two. Let's say the distance between that is given by PI I plus 1. Okay, that's the distance between the two origins. Now we want to find out how do the velocities propagate from one link to another link. Now what will be the velocity of the next link? The velocity of the next link will be its own velocity plus the velocity which is coming from the previous link. Okay, let me just explain this a little bit here. So when we're talking about angular velocity like this, okay, so when this is moving with theta 1 dot, okay, this theta 1 dot will be going on to this link. So the second link will be having its own velocity theta 2 dot plus the theta 1 dot which is coming from the previous link. Similarly, the third fellow will have a theta 3 dot plus theta 1 dot plus theta 2 dot which is going in the forward direction. Okay, so it basically means that this fellow will have some of velocities which are coming in this direction now. So it means even if it itself is not moving, it will still be subjected to a velocity. And two velocities, one is the angular velocities which is theta dot and the other velocity which is V. Okay, so there are two velocities, linear velocities and angular velocities, which move from one link to another link, and we are trying to analyze what is the relationship between the velocities which are moving from one link to another link, so that when the manipulator is moving, we know exactly how the velocities are propagating from one link to another link. Now let's look at the two equations. The first equation is, angular velocity omega I plus 1, I plus 1. I have explained that what is the meaning of I plus 1, I plus 1. It means it's the angular velocity of the frame I plus 1 expressed, this is the link and that is the frame. So the angular velocity of the link I plus 1 expressed in the frame I plus 1, okay, which is equal to I plus 1 Ri into omega II. So this is the angular velocity of the frame omega I expressed in its own frame in the forward direction in the frame I plus 1 plus theta I plus 1, which is its own velocity along the axis Zi plus 1. Okay, so this is the angular velocity of the previous link plus the angular velocity of itself. Okay, so this is the angular velocity of link I plus 1, which is the sum of the angular velocity of the previous link, which is omega I, plus its own angular velocity, which is theta I plus 1. So this gives me the angular velocities. What about the linear velocities? Similarly, linear velocity is I plus 1, I plus 1. So linear velocity of the link I plus 1, which is equal to the rotation matrix into I plus 1 into I into the linear velocity of the previous link, which is Vi I plus 1, plus omega II, which is, we have seen that the linear velocity because of the rotational velocity, which is equal to into Pi plus 1. Okay, so this part is that A omega B cross Pi. Okay, so this is what we just saw. Okay, so Q, there was a Q there, right? Yeah. Okay, so the linear velocities also, because is the sum of the linear velocity of the previous link plus the linear velocity because of the rotational velocity of the previous link. Okay, so this is the linear velocity of the previous link plus this is the linear velocity because of the rotational velocity of the previous link. Okay, so we see there are two equations. This is equation 1 and there is where is my equation 1? This is my equation 1 and this is my equation 2. So this basically tells us how the angular velocities and linear velocities are moving from one link to another link, and using these two equations we can move from one link to another link. Okay, so let's look at a very simple example of 2 degree of freedom planar manipulator, planar robot arm, that is subjected to velocities, and we want to find out what is the velocity of the third frame. Okay, so we have a 2-link manipulator arm here. So this is 2 links. So what do we do? The first thing we do is to put our Z0, Z1, this is X0, this is X1, that's my Z2, that is my Z3, this is X2, X3. Okay, this is having an angular velocity theta 1 dot, and the second fellow is having angular velocity theta 2 dot. Okay, let's say the link lengths are L1 and L2. Let's say this is my link length L1, this is my link length L2. So what we are asked to find is given. So in this problem we are given that the 2 links are having angular velocities theta 1 and theta 2. So given theta 1 dot and theta 2 dot, the 2 angular velocities of the 2 links, and we are asked to find angular velocity of frame 3. Find angular velocity and linear velocity of frame 3. Okay, that's the question. So now what we basically do is we are basically going to use the previous two equations. So the first equation is for the propagation of angular velocities. The second equation is for the propagation of the linear velocities. Okay. Now here also to observe what are the rotation matrices. So the first rotation matrix is T01, which is rotation about sine 1 cos 1, sorry, cos 1 sine 1, sine 1 cos 1, 0 0 1, 0 0, that is 0 0 0 1, this is 0 0 0. This is the first transformation matrix. The second transformation matrix is T 1 to 2, which is given by cos 2 minus sine 2, sine 2 cos 2, 0 0 1 0 0, right? And sorry, there is a link L1 here. Okay, and the third one is equal to T 2 to 3, which is equal to 1 0 0 0 1 0 0 0 0. This is L2 0 0 1. Please note here that frame 2 and frame 3 are in the same direction, but there is only a shift in the a distance of L2 in the x direction. Okay, but there is no rotation between, frame 2 and 3. Okay, there is only a translation. So there is a rotation between frame 1 and 2, but there is no rotation between frame 2 and 3. Okay, so now let's apply these two equations. Now before I apply the equations, let me just write down the two equations so that we don't forget the two equations. So the first equation was omega I plus 1 is equal to I plus 1 Ri into omega II plus theta I plus 1 theta into Zi plus 1. So this is showing the direction. Okay, that's my first equation. The second equation is telling me that Vi plus 1 is equal to I plus 1 R into I into VII plus omega II cross I Pi plus 1. Okay, please note that what I've written here is the expressing frame 1 in terms of frame 0. Okay, but what is written here is that we are going in the forward direction. What I mean is the rotation matrix is basically the rotation matrix is going to give me, this is the rotation matrix, I into I plus 1. That's the meaning of the rotation matrix. So from this frame to this frame. But here what I'm doing is I'm going in the other direction. So this matrix is actually I plus 1 R I. Okay, because I'm going in the other direction now. Okay, so please note that this rotation matrix is actually in the other direction. Okay, so let's start off by saying that we are given theta 1 dot and theta 2 dot. We're given these two. Okay, so let's start applying these two equations uniformly. So when we apply these equations, what do we get? We get that omega 1, we start with link 1, which is equal to, from equation 1 here, the equation of link 0, which is 0, or frame 0, which is 0, plus its own angular velocity, which is theta 1 dot. Okay, so what is the angular velocity of frame 1? It is equal to the angular velocity of the previous frame, which is frame 0, which is doesn't have any angular velocity. It's a fixed frame. So theta 1 0 is 0. So this will be equal to 0 0 theta 1 dot. Okay, because omega 0 is 0. So this is my angular velocity. What about the linear velocity? Linear velocity, again, the velocity of the previous link is 0. So it will only have this one, the second component. And the distance between the origins of frame 0 and frame 1 is the same. That means this is equal to 0 for the first case. So Pi is 0 for the first frame 1 and frame 0. So this will become equal to 0. Okay. What about omega 2? Omega 2 is equal to the velocity of the previous link plus its own velocity. So this is equal to 0 0 theta 1 dot plus theta 2 dot. Okay, and what about the angular velocity? No, sorry, this is the angular velocity. What about the linear velocity? Linear velocity is equal to there's the rotation matrix. So it's the inverse of that, cos 2 sine 2 minus sine 2 cos 2 0 0 1 0 0. And what is omega I cross pi? Omega I cross pi is 0 L1 theta 1 dot 0, which is equal to L1 sine 2 theta 1 dot L1 cos 2 theta 1 dot and 0. Okay, so this part, let me just explain it here. So this part is equal to omega I, which is equal to omega 1 cross pi I plus 1, which is equal to, this is a cross product, so it is I j k. So what is omega 1? Omega 1 is equal to 0 0 theta 1 dot, okay, cross pi. Now it is x in the x direction, right? So there is a distance, pi is the distance of L1 in the x direction, so it is L1 0 0. So this is equal to this minus that, so that is how we are getting this term, L1 theta 1 dot. Okay, so theta 1 dot there. Okay, so I hope you understand how we got this term. So ijk, so plus minus, it will be j into minus of L1 theta 1 dot, so it will become plus L1 theta 1. Okay, okay, so this is how we have got, and we open it, this is what we get. So that is my linear velocity of joint 2. What about angular velocity of joint 3? Omega 3 is equal to the angular velocity of the previous joint, which is omega 2. Okay, so omega 2 is the angular velocity plus its own velocity, which is 0, plus 0. So this is becoming equal to omega 2. What about the linear velocity of joint 3, which is equal to r? Now that's an identity matrix, because frame 3 and frame 2 do not have any rotation, so the rotation matrix is an identity matrix. So if you look at this this term here, this is an identity matrix, so there is no rotation. So there is a rotation matrix, but it's identity. Okay, so identity matrix into the angular velocity of the previous link, which is equal to this one. So this is my angular velocity of the previous link, plus angular velocity because, sorry, the linear velocity because of the previous link now, and the velocity because of this omega I cross pi. So this will become equal to ijk. Okay, let me rub it out here. So that is equal to, so this part is equal to omega 2 into L2. L2 is along x direction, so it is ijk into omega 2. What is omega 2? Omega 2 is theta 1 plus theta 2. Okay, so it's theta 1 plus theta 2 in, so the 0 0 theta 1 plus theta 2 dot. And what is it is 0 0 L2, sorry, just L2 is here, L2 into 0 0. So what will we get there? So omega 3 will be equal to these two terms plus one term here, which is coming because of this one. Okay, so we are getting V3 is equal to L1 sine 2 theta 1 dot into L1 cos 2 theta 1 dot plus L2 theta 1 dot plus theta 2 dot and 0. Okay, so this is how we see that there is a propagation of velocity from one link to another link, and it's the angular velocities which are moving and the linear velocities which are also moving. Okay, so in this rotating system, what we see is that the velocities propagate from one link to another link. Okay, so in the question of dynamics, basically we need to see, okay, so today we looked at velocity propagation from one link to another link, and subsequently we'll be looking at acceleration propagation. We have already seen force propagation from the end effector to the base link in terms of the Jacobian. Now after this we'll have to talk about the inertia matrix. When we talk about planar systems, we talk about moment of inertia. Okay, so if I say a link is rotating about an axis, okay, like in the case of the 2 degree of freedom manipulator I just drew some time back, that is rotating about the axis 1, axis 2. Okay, so there we can talk about moment of inertias. But if you have a rigid body, a three-dimensional rigid body, it can rotate about infinite axis. So there has to be some way of representing the mass distribution of the body. For example, if I were to take this pen and rotate about this axis, so it rotates like this. And if I were to roll it about the central axis, the moments required for both these rotations would be different. And these moments would depend on what? It will depend on the mass distribution of the body now, and depending on where I put the axis. So this basically leads us to the definition of the inertia tensor, which basically gives us an idea of the mass distribution of a body that is required to understand how much moment is required to move the body about or rotate the body about that axis. Okay. So in the next class, we'll move on to looking at the inertia tensor, and then moving on to how to write the dynamic equations of motion, and then finding how that gives us the torques which are acting at the joints when the system is moving. So in terms of dynamics, there are two kinds of dynamics. Like in kinematics, we had two types of kinematics. We had forward kinematics, we had inverse kinematics. Now in dynamics also, you can give the position, velocity and acceleration as an input, and the output is going to be the joint torques which are acting at the joints. Okay, but the inverse of that can be that if I give you the joint torques, can you tell me if I give if suppose I'm fixing a motor and I give so much joint torque as input to the joints, what will be the corresponding position, velocity and acceleration? So one is forward, the other is inverse. So today we'll stop here, and in the next class we'll be moving on to the study of inertia tensor and dynamics. Thank you.